Welcome back, Precalcsters. Today, we are going to start Chapter 2, Section 5, and 2.5 is only a single idea that we're focusing on, and it is the zeros of polynomial functions. Now, when we look at factoring stuff, and I'm going to say polynomials, when we look at factoring stuff, everything that you've ever done, with the exception of some very specific niche types of problems, has been entirely with quadratics. So when you think about grouping, it's grouping with quadratics primarily. Perfect square trinomials, normally with quadratics. Difference of squares, similarly, just with quadratics. Now you could do like x to the fourth minus something else and realize that you have squares there, and it's a little easier of a reach than something like the bell ringer today, the x cubed that doesn't factor. Regular factoring techniques that you guys have learned over and over, factoring or GCF, binomial, trinomial, and then that list, that's all for things that look like x to the 2, x to the 1, and x to the 0, or x to the 2n, x to the n, and x to the 0, where that middle term is half the degree. Now, if I start with an x cubed, I'm not going to have an x to the 1.5 in the middle, because that's not a polynomial anymore. We need whole integers. There was a lot of talking there. Did you guys catch everything I just said? Okay, so just to summarize, just really briefly, you don't have to write this down. You factor stuff that looks like this, where it's degree 2, degree 1, and we don't write it, but there isn't degree 0 here. Now, I'm going to claim that you could use the same techniques. This one doesn't factor, so disregard that exact problem. We'll do it like that. Now it does. You could use the same techniques to factor this, or this, as long as this degree was half as big, like those same techniques work. In quadratics, that always happens. That's why we teach it. There's a lot of different functions that work like this. However, when we start looking at the other piece, the one like from today's bell ringer that we'll re-examine here in a moment, we run into some bigger issues. So right off the bat, we're going to have a really small subsection to start with, or section. The very first section, arguably the most important, but it's also going to be the shortest. We are going to give ourselves what is known as the fundamental theorem of algebra. You will never again see me write this. Dolan, you're in the driver's seat for just a moment. How do you suggest we shorthand the fundamental theorem of algebra? You've got it, man. FTA. Okay. What does it mean for something to be fundamental? Like the basis. Can you tell this is an important idea? Like, obviously, right? Okay. The fundamental theorem of algebra. Now, there are fundamental theorems of calculus as well that we will eventually get to look at. But here it is. If, and this is a really easy theorem to write, if f of x is a polynomial function. So if f of x is a polyfunc of degree n, and what do we mean when we say the degree of a function? The highest power on the variable. Okay. If you give me a polynomial function of degree n, where we'll just specify that n better be greater than 0, otherwise we're just boring, then here it is. Then f of x has at least one, and we could say root or 0 or solution or x-intercept. I'm going to say root in the complex numbers. Okay. Now, this seems weird when we look at it, and this theorem just standing alone, honestly, just right here, isn't that big of a surprise. If I give you something x squared, you're going to find 2 roots. Whether they repeat or not, you're going to find 2 of them. What's strange about this is if I factored something that gives me roots at x equals 2 and 3, are either of those in the complex numbers? So I'm going to write that down because it can be hard to think about. You don't have to do it in pink. This is just our thinking, okay? Let's say I had something that factored like this, and it's a quadratic, and it factored as x minus 2 and x plus 1. What are the roots? So according to according to the fundamental theorem of algebra, I'm claiming and I'm telling you guys that one of these is in the complex numbers.
Oh, 2 plus 0.
This is 2 plus 0i. It's a pure real number because b for the a plus bi was 0, but it is complex. This by itself doesn't really seem that important. Now, it's super duper important, obviously, but what I care more about than this is the corollaries or the follow-up type ideas that come from here. Okay, so essentially, all that this is saying is if you give me a polynomial, we can solve it. That's the big takeaway. We can solve every polynomial. Okay, some corollaries, which, do you guys remember corollary from geometry? Like, you could call it its own theorem, but as a result of this, there's some other stuff that we make sense of. And these are the ones that I would argue are more important for us today. So an immediate corollary, or rather than corollary, I'm sorry, I'm going to make this a star first, asterisk. One thing, what this tells us, worded differently, and we could dig into the specific rigorous stuff that shows this, but I don't think it's as important. A function, and specifically we're talking about polynomials, but if we have a function of degree n, how many roots should we find? Good. A function of degree n, whatever it is, will have n roots. Now, this makes our job so much easier, because I know that if I'm trying to solve and find the roots of a 4th degree function, I'm going to find 4 roots. And I know when I'm done because I found all 4 of them. Okay. Now, an immediate corollary to this. So here's a corollary. And I'm pretty sure there's 2 R's. Corollary. I'm pretty sure there's 2 R's, but I don't have the word written on my page, so I guess we won't know. Unless, anybody in here want a spelling bee before?
No, I'm not talking about
All right, Bruno. Okay, here we go. We don't talk about Bruno. I've never seen them move. Okay, all right. I didn't know. Anyway, corollary. We get what is known as the linear factorization theorem. Now, all these things are going to sound big and scary. They're not, especially once we kind of break them down or decompose them into what it really means. The linear factorization theorem. Super easy to deal with. Okay, right off the bat, let's just break it down. What does it mean to be linear? So the graph is a straight line. Give me an example of an expression or a function that you know is linear. A factor that is linear, maybe. X plus 4 is linear. X minus 2. X plus 7. X plus e, or pi. Doesn't matter, right? It's x to the first power. That's the goal. Okay, so as we're looking at this, the linear factorization theorem tells me, and I'm going to introduce some notation, but before you write it, I want to make sure that we all understand and agree what it means. So I'll write it. You hold off just a second. If, when I write this, what am I saying? Can we all agree that this is the degree of the function f of x? Okay, I'm okay. I want to use this. We should use this for the degree instead of writing degree over and over and over from now on. Okay, if the degree of a function hypothetically is equal to, lost my thought. Cool. If the degree of a function is equal to n, then f of x has n linear factors. Now, this is realistically the exact same thing that we wrote above, and it seems like they're different, but I can move back and forth between a factor and a 0 easily. These are 2 statements just highlighting that. Okay, what we mean by this is if I give you any function, and it could be super ugly, we could factor it down into something that looks like this. A, and then x minus, I'm just going to say c sub 1 for my first root at x equals c sub 1. And then another one could be x minus c sub 2, x minus c sub 3, and then dot, dot, dot. What's the last one that I would write? X minus c sub what? There is a correct answer here. N. There are n roots. There are n linear factors. Now, I'm not going to write this one because we'll see examples where we don't do this every time. And there's a reason we don't do it necessarily every single time. Did I ever tell you that these had to all be real? No. So if I had a factor of x squared plus 1, the sum of two squares, we wouldn't normally break it down any further. But you could factor the sum of two squares if you would use the complex numbers. It'd be x minus I, x plus I, and you would get that out of it. This doesn't specify if they're real or imaginary or a mix thereof. It just says you could do it in all the linears. Okay. All right. There's a lot of big ideas on the board right now. Questions about any of them? Because we're going to move on to another big idea, like immediately. These feel okay. All right. So here we go. Looking at this, we're going to jump right in. I'm going to skip a simple example. And a really quick question. What color are rational numbers?
Right.
Okay.
Yeah.
Red for rational. Cool. Here we go. New topic, same section. We're going to be looking at the rational zero test. The rational zero test. Now, because this word will show up so frequently, I think it's on the board behind me. Does anybody know how we write the rational numbers? It might not be on the board behind me. I don't know if it is. Oh, it's not there. Bummer. What letter is it? A blackboard something. What's a ratio? It's a fraction. And fraction is just a different way to write a division, right? We'll get there. What do you call the answer to a division problem?
Oh, the Q.
It's the
I
Q.
think we talked about that.
I think so too. I don't know why I didn't write it up there.
It's on the top.
Hey, there's just nothing listed on it. Okay. This is what you can use for rational. Now, just so you guys know, and you'll see why here in a second, the rational zero test, that's its formal name. I typically refer to it as something different. I call these PQ lists. And you will see why here in a second. This is ugly. This is maybe ugly, but we'll take a look. All right. We need like 30 seconds of writing, or probably like 2 minutes of writing. And there's not a ton, but it gets ugly. Cool. We'll do a really quick brain break here as soon as we get this done, and then we'll do a couple examples. Okay, if the function, and we're going to say it is defined as this wonderful mess, a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot, 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 all the way until we get to a sub 1x plus a sub 0, or a naught, if you will. And we're going to pause here first, because I think we've talked about this, but I want to reaffirm something about it. Davian, I'm not going to make you move, but if you want to see closer, there are open desks. That's ugly, right? It just looks ugly. Do you remember what that really says? Like, it's ugly because the indexes, the little n's that we use. This is just a number. So this could be a whatever. And this is just to the power of n. This is the biggest degree, right? The biggest term. And then this one is just one less. So if this were x cubed, something x cubed plus something x squared, this is just a polynomial. It's the general way to write it. It looks ugly. That's it. Okay. If you give me this function, and it's a nice polynomial like this, with integer coefficients, which I'm not going to specify because that's what it means to be a polynomial, then every rational zero of f has the form, and we're going to leave a colon here, every single rational zero. Any one that can be written as a fraction will look exactly like this. All the zeros are just x. It will equal, and this is going to look ugly for a second, p over q. Hence the name PQ list. Where the natural question is, well, what on earth are p and q in this situation? I'm going to make sure everybody's caught up writing before we write the next part. Okay, when we look at this, we have P over Q, where, couple things. The first is that the greatest common factor between P and Q, it has to be 1, which is just the mathy way of saying these are simplified fractions. And these numbers P are chosen from a factor of the constant term. P is a factor of, and instead of writing the constant term, in our lovely form here, this general polynomial, which one of those is constant? It doesn't have a variable on it. Only one number up there that doesn't have a variable. Or it's going to look like a letter. Does this one have an x to some power connected?
Yes.
The first one does. Does the second?
Yes.
Does the second to the last have a variable in it? It does. It has x to the 1. Does this have a variable?
No.
So if it doesn't have a variable, it doesn't vary. Everybody agree with that? And if it doesn't vary, we say it is constant. This is my constant. They're just factors of a sub 0, or a naught, the constant. And Q is simply a factor of, and I'm going to write, what? Not 2, weird. A sub n, which I'll do the same thing here. Based on that general polynomial, what on earth is an easier way to refer to a sub n? One more time? So a sub n is not a variable. It's the number connected to the first one, right? Gosh, when we had a number connected to the biggest power of x and there was a name for it.
Coefficient.
What kind of coefficient? It is the leading coefficient, exactly. LC, for leading coefficient. Okay, now, does everybody remember how to synthetically divide?
Yes.
Fantastic. We're going to need it. Okay. So I will be doing a bit of calculator stuff. We're going to use this. Now, your text, and every text for that matter, might have slightly different ways of writing this out. That's okay, right? It's all just notation stuff. Of course, as your teacher, I'm going to show you the way that I would recommend to do it. And it's very similar to the text. It's not exact. But let's dig in. So, to begin with, the rational zero test. We're going to hate this for one time. That's it. We will hate it once. Okay, so we're going to do a whole problem together. And our example is just simply going to be find all zeros. Okay, that's it. We're just finding the zeros of a function. Now, your calculator, just for the record, it could graph the function and it could find the x-intercepts. That's not what we're going to use our calculator for, because I don't care that your calculator can graph. All right, bless you. So remember, when we gave the bell ringer today, you guys ended with saying you, what?
Can't do it yet.
You can't yet. We're about to. Check it out. Let's look at that exact function. F of x is equal to x cubed minus 7x minus 6. Now, legitimately, this problem's going to take us like 15 or so minutes. They don't really. Like, realistically, when you're doing these on your own, they won't. But we're going to make sure we hit every part of it as clear as possible so that when you do it on your own, that 15 to 20 minute problem becomes like a 5-minute max. Okay, so let's check it out. The very first thing, and I don't typically do like ordered lists and things of that nature. This time I kind of do. Step 1 is I want us to identify the possible rational roots. Okay, because if there is a rational root anywhere, a 1/2 or even a 1 or a 2, those are all rational numbers, I can find them. So here's where this part, and we'll decide, we're not in Algebra 2. Have you guys seen this before? Does it feel familiar? Okay, I'm not convinced you haven't, but maybe it just doesn't look familiar yet. Help me out here. What is P in this situation? So factors of 6. Now, I'm going to write this a couple different ways. This is legitimately what it is. It is the factors of the constant term right here, 6. Now, when we do these, I'm going to write this again, P equals. I know it's negative, but is that your issue? Don't worry, we're going to hit it. We're going to write P equals the negative part, we don't have to worry about it because we get plus or minus. I don't know the sign of it. I just know that it's a factor, whether it's positive or negative. So help me out here. We're going to count up in an orderly fashion. P is the factors of 6, and I'm just going to say here's the factors of 6. If it is more natural, that's how I'd normally do it, but I want to be really clear. Okay, what are the factors of 6, starting at the lowest? 1 goes into 6. 2, 3, and 6. These are all the factors of 6. I'm going to put the P back there just so it makes more sense. Everybody cool with that first step? Okay, I also want us to find Q. And I won't write it out this time, but how do we get Q? The factors of what? 1 in this case. And I will write it. I lied to you. The factor or factors of the leading coefficient, which is a 1 connected to this. Okay, feels silly, but what are the factors of 1? Or negative 1, plus or minus. Okay. There's 8 possibilities that we have right now. And it may not really seem like it, but sorry? Kind of. Only gross if we make you write them all out, like I'm about to. Okay. These are the possible rational roots. We're building up to it. So I know that it's not just P and it's not just Q. If you look at the rational zero test, all the possible rational roots will be of the form P over Q, right? So realistically, this is all just thought process that goes into it. This I normally won't include. Like, I'll think this part out. So here we go. Possible rationals. And this is my shorthand, possible rational. Plus or minus. It's P over Q, right? What are the possibilities for P? And I'm just going to put plus or minus in front so I don't have to deal with all of them. We already decided 1, 2, 3, and 6. Do you guys agree with that? And the factors of Q, the factors of 1, there's only 1 this time. Now, here's the deal. I don't really want to make you write them all out, but I am going to make us count them all because there's 8 numbers up here. Can you guys see 8 numbers?
Yeah.
Positive 1 over 1, 2 over 2, 2 over 1, 3 over 1, 6 over 1. Or negative 1 over 1, 2 over 1, 3 over 1, 6 over 1. 8 possibilities. Now, I don't know which one it is, but I know that if there are rational roots, it's going to be one of these numbers, at least one of them. Now, we will use a calculator after this. After this one problem, I'll show you at the end or here in a minute how we check this on the calculator. But you don't have to write it, but I do want to make sure all of our numbers are there. So check it out. I would not write this if I were you. You can. I need to check 1, 2, 3, 6, negative 1, negative 2, negative 3, negative 6. Those are the 8 numbers. Okay. Don't really care where we start, but if I have the list here, I will be able to make sense of it. Where would you like to check first? There's not a right answer. I know where I would start. 1. Okay. So eventually it's going to suck. Like if I tried to plug in a 6 cubed would be terrible, right? The good news is that if this is a root, it means that when I divide by x minus 1, for example, the remainder would be 0. So check it out. I'm going to check 1, and I'm just going to plug it in. I'm going to plug in a 1. And we're going to do this fancy synthetic substitution, which is what I was hoping you guys did on your test yesterday, but you might not have. I should not have probably said, no, whatever. What are these numbers? What goes here based on our function f? 1x cubed. How many x squareds? Are you sure, Matilda, I think? How many x squareds? 0. How many x's? Negative 7. And how many x to the zeros or constant? Negative 6. Okay. If this is a 0, I have found my first factor. Let's try. 1, 1, 1, 1. Negative 6. Negative 6. Okay. Not a root. Bummer. We've tried it. What would you try next? Because I add them straight down. Agreed. Negative 1 or 2? You want to try 2? So here, we're going to divvy it up. 2? Okay, weird.
Okay.
2. Negative 1. Negative 2. I'm not going to do everybody. Pick a number to check it. Something that's not. Maybe 2 is a good choice to check.
2 is a very good choice.
You should try 2. And I'm going to make a comment here. The sad face, I think it expresses it, but so you guys said to try 2. And this is really step 2. We're checking each. I didn't write that down. 2. So we'll try. Did 2 work?
No.
No.
I was really excited about it. 1, 1, 2, 2, -5, -10. I think it's -16, though, Addison. Am I wrong?
2 times 2 is 4.
That's probably true. Scratch that, Addison, you were right, I was wrong. And in fact, I assume everybody was right and I was wrong. It is -12. Okay, 2 didn't work. So x equals 2 is not a solution. 3? Well, let's try. 3. Now, we have a small list right now.
I did a larger one.
Indeed.
Gross.
Hey, 3 works. Now, there might be another one. Okay, there is another one that will work. But we found it. Is it possible that whatever order you pick to check, 1, -1, 2, -2, you don't find it until the very end? So like in this problem, if it had, like, conceivably, I could have checked 7 things first that failed until I got to the one that worked. Okay, here's the deal. I think you guys know how to synthetically divide. I do not think you need to do hours of synthetic division every night when you're doing these problems. I want you to grab your calculator. On your calculator, I want us to go in. Do you guys know how to use these pretty well or not really? Okay, so we're going to use them. I'm going to go into y equals, and I'm going to type my function, x cubed minus 7x minus 6. And I'm going to hit enter. And I'm going to double check to make sure I have the right function. Do we agree? Okay. If you have this, and I just really want to stress this because calculators are like the bane of my existence. If you get behind, tell me then. Don't wait until we're 3 steps ahead to say, oh, wait, what did you do before that? Nope. Do it now. Everybody have this?
Yes.
Okay, we're going back to the home screen. Now, there's a variety of ways that we can work with this. I'm going to go back, and I want you to do the same, and we're going to double dip. Good question. First thing, I want you all to verify with y equals, do we all have this defined as y1?
Yes.
Okay, second, and then quit will get me back to the home screen. Cool. All right. Now, there's a variety of ways to do this. If I wanted you to find f of 1, somebody could conceivably do this. And I think that this, like, you might not have to do it for the number 1, but you could do this to get the value. That's f of 1, right? And it's kind of tedious. I think it's -12. It is. Here's what I want us to do. Do you guys agree that y is typically a variable? And that there's a button right here that says vars, which is variables. Click that vars button. You should have this window on your screen.
No.
Everybody have this. Anybody not have this window? That's a better way to do it. Okay, again, if you are quietly just not telling me you don't know, the vars button's right here. I just click it. Now, you guys all know what tabs are on like Google Chrome or something. Do you see there's 2 tabs at the top? There's vars, which is where we are, and there's y vars. We just type something in for y, right? I'm going to go 1 to the right to get to y variables. Now, I want to treat this thing like it's a function. I'm going to, now that I'm in y vars, I'm going to hit enter on function. Now, for calculator stuff, 2 options. I can either hit 1, and it will select that, or I can just hit enter on the one that's highlighted. So I'm going to hit 1, and we're going to get to the same screen. Or enter. Do we all have this in front of us now? Where did we store that last function? I'm going to hit y1. Now, for this, the notation doesn't work super well, and I just want to check something. I'll come back to the calculator. If I said this, y is 2x plus 3, hypothetically. If I said find me y of 3, this isn't normal notation, but do you understand what I'm asking you to do? What do you think I'm asking you to do? So just like this? No different than if instead of this I'd said f of x. And then f of 3 makes more sense. Like we can kind of move between. Your calculator doesn't understand f. However, your calculator does understand y1. Now, we checked 1, 2, and 3. That was the order we went, right? Okay, you have to, and I want everybody's ears open. If you're playing with the calculator, make sure you catch this. You have to do the synthetic division by hand for the one that works. I need one synthetic division on every problem. Okay, instead of doing 3, which is what it took on this one, or 10 on another one, check it out. I'm going to do those exact same 3. I'm going to do y1 and then of 1. You have to include the parentheses. We know the answer is negative 12. I'm going to hit enter. It's negative 12. I need it to be a 0 to see I found a root, right? Now, if you don't want to have to go back through the menu, right now, I don't have it typed in and I can't just do the same thing. Hit second and enter. It just recopies the previous line. So y1 of 1 didn't work. So if I was looking at this list on my homework or whatever, I would say, okay, you're done. Get out of here. Didn't work. You're done. There we go. Y1 of what is next? 2. Is that 0? Bummer. You're also done. Y1 of 3. Is that 0?
Yes.
Oh my gosh. This is the first one that I would write down. Once I've done this on my calculator, I will jump back over here and I will do the synthetic division with 3. We happen to have already done it because I made you guys do it, but we found it. Now, here's where all these pieces come back together. Right now, we checked it until we found one that worked, and it worked. This step, your book does not see, but it will look exactly like stuff we've been doing. If I'm doing step 1, step 2, step 3 is write f of x, as partially factored. Now, what I mean by that is we can go backward from where we just were. Right now, whatever f of x was doesn't really matter to me. Did we just now find a root? We found x equals 3 was a root, right? What's the factor that we get from x equals 3 being a root? X minus 3 was our factor. Now, that idea is really important. If x equals a is a root, then x minus a is a factor. That's what I'm using, that same statement. So check it out. One of my factors, can you tell me with confidence what it is? X minus 3. And that last little comment, this is what I'm using. If x equals a is a root, then x minus a is factor. And I'm trying to hit this idea really hard in my Algebra 2 class right now. If you can accept this as true, I'm cool with it. But think about what happens the other way. If I get to a factor x minus 3, for example, is equal to 0, to solve it, I just add 3, right? And I get x equals 3, which is essentially what we just had. If I said, oh, what do I do to make this 0 on this side? Do you agree we just subtract 3 from each side? And now I can see the factor. Like, I'm just rearranging it. Like, it's all here. Okay. That is just a little sidestep. One of my factors, you guys were correct, is x minus 3. Is there another factor that we got out of this? Negative. So timeout before we get there, and I know that you might have found it on the calculator or you might have seen it, but we're going to pretend like it didn't. Based on this, do we have another factor? So x minus 3, because remember it's the opposite here. These are the coefficients of our quotient, right?
Oh.
We started with x cubed. Where are we now? 1
X squared
x squared
plus 3x
plus 3x
plus 2.
plus 2. This is the factor that we checked, and this is the quotient. So the divisor, I'm trying to remember d of x and q of x. Do we all remember doing that? So I'm not even asking for last year, and it's okay if not, but we did something almost identical to this, like all throughout 2.3. Okay, so it's been a week or two, but if you look back, we did this. So now, am I done? No. Whether you call this step 4 or not, I don't know. I'm going to call it 4. What do you think we should do? Keep factoring. Okay. Boom. Keep factoring. That's it. Does this one factor any further? X minus 3. Notice the linear factorization theorem that we wrote earlier said I can find linear factors. Here's a linear factor. It's prime. Yes, ma'am.
Wait, where'd you get Q of X again?
This is just my quotient. 1, if I started with x cubed and I divided by x, this is my 1x cubed, squared, sorry. 3x squared, or gosh, x, I'm off by 1. Okay, so let's keep factoring. X minus 3 doesn't go any further, so I'm just going to make sure I don't lose it, but I don't have to do anything else to it. This one, run me through the list. Is there a GCF of that trinomial? Nah. Is it a binomial? No, it's not. This one is, for sure. But I did say, is this trinomial a binomial? Definitely not. What's the leading coefficient? Why do I care? There's a shortcut waiting for me. If I take the first a, 1 times 2, it's 2. Can you guys find factors of 2 that add up to 3? They're the only factors, right? Now, if and only if this is a 1, we don't have to do all the fancy grouping. It's x, what were those two numbers? Plus 1 and positive 2. Check it out. We now have a completely factored version of that.
How'd you do the last step?
Let me move this down. What I'm not doing is grouping it because do you agree there's a 1 here? So it's 1 times 2, 2. And then we find factors 1 and 2. And then if you wanted to group it, we could rewrite this as a four-nomial. But every time, if and only if this is a 1, we just jump right to these numbers right here with x. It's just a handy shortcut. Okay, we're not really done with the question yet, though, are we? What was the actual question? So can we find them now?
Yes.
Instead of setting f of x here, I'm trying to find when f of x is equal to what if I'm looking for the roots? Or the x-intercepts, the solutions, the zeros. Now just keep factoring and solve is what I'm going to say. Okay, here we go. ZPP, the zero product property. What value of x makes this factor equal to 0? What value of x makes... What value of x? 2? Okay. Check this out. We started with a function of what degree? How many roots did we find?
3.
I'm convinced. We're done. Now, we will use this eventually to save on graphing stuff because it turns out it's a huge help. Do you believe that if we graph the original, these are the x-intercepts, or do I need to show it on Desmos? They are the x-intercepts. You can check it on Desmos. Okay, that problem took legitimately 20 minutes. Do you want to see that they don't really? Okay, I'm not going to give us homework tonight because I want to make sure that we can work through this tomorrow. Addison, I'll give you the assignment today if you want to work it on the plane or whatever.
Okay.
Don't know if you want to. But check it out. Let's do one more real quick. Okay, we are going to use calculators and we're going to divvy up the labor. I want to do one more function that's just a little uglier. This one on B, and we're going to work all the way up till 30, but we're going to finish this problem, bigger, harder problem, in 10 minutes. Easy. So here we go. I want f of x, this time is the disaster, 3x cubed minus 20x squared plus 23x plus 10. Now, when we do this, you never have to do everything exactly like I do. If you have an alternative that you want to use, check with me to make sure I can agree that we're doing the same thing. But very few, I try pretty hard to not just say, hey guys, watch me do a problem. And we're not going to do that this time either. But I am going to be much more conservative about what I write down. I will write way less. I'm not going to annotate near as much here. If you have questions, I'll add annotations and stuff. Okay, first thing. When we do this, I don't remember what step 1 is because I don't usually do it as steps. What did we say step 1 was on the previous problem?
Possible Q thing.
So check it out. I'm just going to jump right there. Possible, rational is that word. Q thing or rational, roots. Now, notice I haven't said P equals and Q equals, I know that they're going to have the form plus or minus, and I know that it's going to be a fraction. The numerator of this fraction are factors of what? And you might need to look at your notes. Like, if you don't have it ready to fire off, I'm good with that. That's expected. Red, we made eye contact. How do we find the P, the numerator part? Okay, what are the factors of 10? 1, 2, 5, 10. Okay, how do we find the Q part?
Factors of 3.
What are they?
1, 3.
Okay, follow up. You do not have to write them all. But I want to know how many possible numbers could we wind up checking if everything went just completely wrong and we made every wrong guess until the very end? 16. Okay, just to be really clear. Positive. I'm only going to do the positives and we get negative words. I get a lot of singing stuff on my YouTube and stuff, and there's a song that I've been singing that I don't know the words to all of it, but it's about enunciating when one sings, because a lot of time people slur their words together when they sing, right? Like people get lazy. I like to enunciate every single thing I say. Bum, ba-dum, bum, bum, bum. Anyway, all right. I will try to enunciate is the whole point. What are the 8 positives? 1 over? So 1 over 1, 2 over 1, 5 over 1, 10 over 1. Then I'm just going to restart. 1 over, 2 over, 5 over 3, and 10 over 3. Now, sometimes you will wind up seeing that you'll get 2 over 1 in one list, and then maybe down the list you'll get 4 over 2, and you'll recognize, oh, it's the same number, and you actually saved one. But there's a lot of them. Okay, here's what I think we should do. I don't want to do synthetic divisions. The race is on. We're all going to type in this function into our calculator. And we have 3x cubed. And I'm going to clear everything first. 3x cubed. Sorry, I don't need to talk out loud. Once you have it typed in, start checking your numbers. And I know where I'm going to start. Plus 10. If the second you find one, shout it out. I'm cool. 2. 2. So let's just use one of them. And we're like, I'm only doing this to save time. I don't want you guys to just use a calculator to find them all. I'm just going to use the first one. Let's use 2. Because theoretically, you should be doing this without a calculator. 2 over 1 seemingly will work. I need to verify that, because if I just type something in wrong in the calculator, I'm not going to trust that. So let's check if that's true. 3. Thank you for that. That's super helpful. Like, realistically, thank you. It gave me 0, which is a good sign. Now, in the first few sections, when we were going through stuff, something that I included every single time was this next statement. I always made us say, hey, check it out. This was 0. That means x minus 2 was a factor. So my very next line, once I'm here, I'm just going to rewrite my factored form of f. What's the first factor that we guarantee just worked? X minus 2, because x equals 2 is the root, x minus 2 is the factor. Okay, what is the other factor that we now see just hanging out there? Red, did you get it to work with 2? Okay. So purely out of curiosity, you're not in trouble, but what are you still on the calculator for?
Oh, I made a mistake.
Okay.
Squared.
Okay, no worries. What's the other factor here?
3x squared minus 14x minus 5.
And that's there. Now, if we're trying to completely factor this, this piece is already a prime linear factor. I'm now going to factor this one. Unfortunately, I don't think the shortcut's here. Why? How can I tell that? That pesky 3. So we need factors of negative 15 that multiply to be negative 14. So 1 and 15, where that's my negative. Okay. There's no shortcut. Don't use a shortcut. We have to group it, right? I'm going to do a little bit of scratch work over here just so it looks a little bit nicer. I'm going to rewrite this, but instead of minus 14x, what am I going to put in that big awkward gap in the middle?
Negative 15x plus x.
And it's awkward gapping, but I'm fine with that. Okay, this is our grouping process. What comes out of that first and second? 3x minus 5. What do I take out of this to leave behind an x minus 5? Kind of a trick question. A 1. The only time that I'm ever going to want you to factor out a 1 of something is in this situation. Is this enough to see my other factors? Okay, I wish I had done all my scratch work over here, but check it out. We have x minus 2, and now we have, what's another factor?
X plus 1.
3x plus 1 and x minus 5. So that's my function f of x. From this, a little bit of mental math, if we set each factor equal to 0, we're going to find all 3 roots of my cubic function. X equals 2.
1.
Negative 1/3. 5. Now, we didn't see it today, and Addison, this is more geared toward you because you won't be here when we work on it. Is it possible that I give us something bigger than a cubic?
Yeah.
Now, I don't want you to necessarily just do this exact problem here, and in fact, I didn't do this problem. What I want you to be aware of, Addison, and this is everybody, but I'll read this tomorrow, is if this thing came out as a cubic again that I couldn't group or anything like that, is it possible that I need to do another PQ list?
Yes.
It could do 2 of them for sure. This problem right here, did that seem okay?
Is it just that one? Like it's only the two that works?
What's up?
Was it only the two that worked?
Somebody else wanted me to use 5 because they found it worked too. But the calculator part, if you find it and you see 5 works, you probably wouldn't have guessed 1/3 ever unless it came out of your list. This problem,
Oh, I see.
yep, so I'd say go until you get the first one, Addison, and then stop there.
All right.
Yep, cool. All right, later Raiders, come tomorrow with your work hats on. Not hard hats, work hats.